Okay, today we will talk about free energy. This is something related to thermodynamics. This is extremely important. If you ever continue on and want to go deeper into soil chemistry, you need to know something about the thermodynamics. But this will be short lecture and simple one because we can't go deep into this subject. Some of the material you probably already know from if you ever studied physical chemistry, and some of you might not have heard of it, but it should be hopefully familiar with all of you. So we'll talk about the free energy. The thermodynamic term of widest use in soil chemistry is the Gibbs free energy. That's where the G comes from, Gibbs free energy, the scientist who named it or he defined this term. Sometimes some textbooks and some scientists call it also F because it's the free energy. So free energy or Gibbs free energy. The energy of a substance or a reaction that at constant temperature and pressure is available for subsequent use. So if we want to define it, it's the energy of a substance or reaction that is available for subsequent use. The conditions so that this definition is correct, it has to be at constant temperature and pressure. And as we will see, most of the time, most of the reactions are carried out at room temperature. So it's basically constant temperature, 298.15 Kelvin or 25 Celsius. And the atmospheric pressure, which is in the laboratories, 1 atmosphere. So they are carried out at constant temperature and pressure. And so that energy of a substance or a reaction, which is available for subsequent use, for use later, is directly related to this delta G, or the free energy, or the energy that we define. It's related to the activity or chemical potential of compounds, ions, elements. The energy of formation of compounds, we'll talk about it in a minute. Also, it should be hopefully familiar to you. The equilibrium constant of a reaction, which you know, K for any reaction, and the electrode potential. Electrode potential, this is extremely important. It's studied when you're interested in oxidation reduction reactions that takes place, and those we are interested in the ones that take place in the soil. The spontaneity of a reaction involves two thermodynamic concepts, enthalpy and entropy. Again, these should be known terms for you, hopefully, if you ever studied in your chemistry or some aspect of physical chemistry. So the spontaneity, that means if the reaction will take place, will start without interference, without giving energy, no heating, no other energy that is required for it to go on. For any reaction to take place, if we say it's spontaneous by its own, when you mix the reactants, the reaction starts, it takes place right away. So that's spontaneity. So the spontaneity of a reaction involves two thermodynamic concepts, enthalpy and entropy. How can we use delta H, which is enthalpy, delta S, the entropy, to predict if a reaction will be spontaneous? That's eventually all our interest, especially in this particular lecture, will be finally to arrive to a relationship between delta G and K and how the reaction is going to take place. So how can we use delta H, delta? Remember, we don't say usually H and S in most cases. We say because we can measure only the changes in these properties. Delta H, delta S, the change in it from one condition to another, when before the reaction starts it and at the end of the reaction. Gibbs free energy, G, is defined as G equals H enthalpy minus Ts. S, the entropy. T is the absolute temperature, the Kelvin temperature, or absolute, for a process at constant temperature and pressure. Remember, we already defined that it has to be at constant temperature and pressure. Delta G equals delta H minus T delta S. It comes from the original definition. Here we said G equals H minus Ts. Delta G equals delta H minus T delta S. Of course, if we are at constant temperature, we cannot say delta T. So we say T, the temperature that the reaction is taking place at. And we measure delta H and delta S. If both T and P are constant, like we said, that's the relationship usually we are interested in, the relationship between the sign of delta G and the spontaneity of a reaction is as follows. This is very important, and you should know that. You probably should have known that, but I'm reviewing this because it's very important for any soil chemist to understand something about thermodynamics. If delta G is negative, when you calculate delta G for the reaction is spontaneous in the forward reaction. That means it will go to the right as you have written it. If you write a certain reaction and you calculate delta G in that reaction, for that reaction in the shape it's written, then we say if it is negative, that delta G, then it's spontaneous in the forward reaction. So it will go from left to right as you have written it. If delta G is 0, the reaction is at equilibrium. That means finished, it's finished. It's not going back and forth. It might be going back and forth, but at the same speed. You don't feel it, you don't know it, but it's constant, so it's at equilibrium. If delta G is positive, the reaction is spontaneous in the reverse direction. So if you have written a reaction certain way, and then you calculated delta G, and you find that it's positive, then that reaction is going to go from right to left, not from left to right as it's written. It will be in the reverse direction. How do we use delta G 0, which is the standard Gibbs energy, to calculate delta G, which can be under any conditions, under non-standard conditions? So we need to know this because this can be calculated and known, because lots of values we can obtain them for the standard conditions. But if you have non-standard conditions, how do you get delta G from delta G 0? How do we relate the value of delta G 0 to the value of equilibrium constant of a reaction? That's what really we're interested in, and then we will see the value of that, the importance of this relationship, the relationship between delta G 0 of a reaction and its K, the K of equilibrium. For any chemical process, the relationship between delta G 0 and delta G is given by this. Again, this is in chemistry and thermodynamics and physical chemistry, known relationships. Delta G under non-standard conditions equal delta G 0, which is for the standard conditions, plus RT, L, and Q. R is what we call the ideal gas constant. R, universal, sometimes some people also call it the universal gas constant or the ideal gas constant. It has a known value. And the known value will be depending on what kind of units you use. So if we are using joule per mole over mole times K Kelvin, temperature, the value of it is 8.314. For these, later we will see it has a different value if you use the calorie system. T is the absolute temperature, is T, Kelvin, or the absolute temperature. Q is the reaction quotient. What's the reaction quotient? Now at equilibrium, when you write K equals, you multiply the activities of the products and divide them by the activities, the multiplication of the activities of the reactants. Now Q, it means for any reaction, it doesn't matter if it is at equilibrium or not. So it will be multiplication of the activities of the products divided by multiplication of the activities of the reactants. So that's quotient. Quotient is in Arabic al-kasr. You divide something over something. Quotient, same thing as that's the division of one thing over another. So under standard conditions, all concentrations are equal to 1. That's by definition. That's why, sorry, so that's why it is called standard. If all standards, under standards, all the concentrations are equal to 1, then Q equals 1. If you multiply the activities of the reactants, and each one of them, the value of it is 1, divided by the multiplication of the activities of the reactants. Sorry if I said it the products over the reactants. Then everyone is 1. So 1 times 1 times 1 are divided by 1 by 1. So Q is value equals 1. And what do we know about the logarithm ln Q or log 1? Always 0. So this will be 0. Multiply by this, it's 0. So this equals this. So then delta G equals delta G 0, or standard free Gibbs free energy. So at equilibrium, delta G equals delta G 0 plus RT ln Q. We already said, if you remember, we said at equilibrium earlier, we said at equilibrium delta G equals 0. Okay, this is how we know the spontaneity of it. Remember how at equilibrium, or it's going to the right, going to the left from the value of delta G. So if it's at equilibrium, delta G equals 0. So 0 equals delta G 0 plus RT ln Q. So then you take this one to the other side, or take these to the other side, becomes negative. When you move one thing from the right side to the left side, it changes sign. So delta G 0 equals minus RT ln K. So we can, from this, we can see if delta G 0 is negative, this is a negative value. Of course, negative equals negative. So that means you divide them by each other, becomes positive. So that means this has to be a positive value, ln K greater than 1. Okay, if this becomes positive, how can this be positive? This K has to be greater than 1. If delta G 0 is 0, then K equals 1. How can we get this? If this is 0, how could this be 0? This has to be 0. R cannot be 0. T cannot be 0. So ln K has to be 0. And when do we have ln K 0? ln of 1. So K equals 1. If delta G 0, if delta G standard is positive, then K is less than. This will be a fraction to give you a positive one, okay? So if this is positive value, so this has to be negative, and the only way it can be negative is this one to be a fraction, which is less than 1. Okay, conventions used in establishing standard free energies. The conventions, these are approved and agreed upon by scientists. This we do not have to guess, we just have to know. Solid, the standard free energy for a standard solid, it's pure solid, which means, remember, we said pure is not like the impurity mixed with it. Pure in structure, pure in its nature, in its the way it's made, not something outside, not mixed with something external. That's not the purity we talk about. The purity of the compound, the metal, whatever it is we're interested in, that's the purity of that solid. Liquid, pure liquid, again, it cannot be like solutions mixed with other things, the pure liquid. Gas, at 1 atmospheric pressure, that's the standard conditions. Solution, if it's a solution, 1 molar concentration, that's the standard. Elements, always defined as 0. It doesn't matter, as long as it's, remember, elements, not ion. The elements are defined as 0. Okay, we come eventually closer to what we need to learn out of this, really. What is the final thing we're interested in? Remember to relate delta G 0 to the K, or the equilibrium constant of any reaction. The standard free energies of formation are useful in calculating the standard free energies changes for chemical processes. Okay, there are 2 different things we have to concentrate on. Standard free energy changes of a process, which is a reaction, delta G of a reaction, but if you put F here, small f, that is the formation. That's only for elements, compounds, ions that enter into the reaction or are the products of reaction. So the standard free energies of formation are useful in calculating the standard free energy changes for a chemical process. Chemical process we're interested in are the reactions. So delta G0 of any reaction equals the summation of N. These are stoichiometric, remember, factors that we multiply by when you balance an equation. Delta G0 of formation of all the products minus the summation of M, of course, the different values of the stoichiometric factors, delta G0 of formation of reactant. Now the standard G0 of formation of any ion, element, compound, they are found in the literature. We can obtain these values. They are known. Okay, so again, this is something you don't have to guess. We don't have to, they have been calculated and known and tabulated in chemistry books. If delta G0 is less than 0, the reaction is spontaneous in the forward reaction. We already said this, remember earlier. If delta G0 greater than 0, then the reaction is spontaneous in the reverse direction. We already know this information. Okay, so again, we write it again and see how we can simplify it. Delta G0 of reaction equals summation of delta G0 of formation of all the products. You subtract from it the summation of delta G0 of formation of all the reactants, then to obtain the delta G of the reaction, where the summation delta G0 of formation is the standard free energy of formation of all the products and reactants. The standard free energy change of reaction is related to the equilibrium constant pi. We already have seen that. Delta G0 of R equals minus RT ln K. Remember, we said usually the reactions are carried out at constant temperature, constant pressure. R is the universal gas constant. A while ago I told you, international, universal, ideal, universal, all the same for this value of R. The gas constant, T, is the absolute temperature, Kelvin, at 298.15. Told you this is considered the room temperature. If you change this to Celsius, it's 25 Celsius. So delta G0 of R equals the value of R, which is known under these time if we use the joule, not the calories of the units of energy. Okay, so joule, K to the minus 1, remember over, a while ago we said joule over K times mole multiplied by the temperature minus R, this is the value of R, T 298.15, now most of the time it's much easier to use the natural log, the normal log, which is to the base 10, instead of ln, which is to the base e. So to change ln k to log k, we multiply by this factor. This is simple conversion from ln to log k. Remember, log k, because it's to the base 10, will be a smaller number. So you have to multiply it by bigger number to go back. So ln will be, of course, larger number than log k. So that's why we multiply by 2.303 log k. So then we have, from this log k, we multiply all these numbers, you come up with a constant. So we have now a relationship between log k0 equals minus delta G0 over, for the reaction, over 5.71. This is, under these conditions, a constant known relationship. So if you want to calculate K, and in your textbooks, although this already I have discussed it for the undergraduate, those whom I taught, you should know that, but there are examples and there is a table that has values of those. Go over them and see how this is calculated. It's a very simple application of this type of calculation. Now, so if we know the values of delta G of formation of all the products and reactants in any reaction we're interested in, we calculate from that delta G0 for that reaction. From that, we can calculate the value of K for that. So we have log K, and from log K, we can calculate K. Like I said, there are two different systems that are used. In the old textbooks, we have seen so many values given in the calorie. They used to deal more with the calorie instead of the joule. So the value, the only thing that will change will be the value of R. It will have a different value. 298.15 is still the same. This is still the same. So this is exactly like we did earlier. Delta G0 for the reaction equals summation of delta G0 formation of the products minus summation of delta G0 for the reactants, where delta G0 is the standard free energy of formation. Repetition of what we already have said. The standard free energy change of reaction is related to the equilibrium constant by delta G0 of the reaction equals minus RT ln K. R is the universal gas constant. T is the absolute temperature at 298.15, which is, we set the room temperature that most reactions in the laboratory are carried out at. So again, we calculate find out the relationship between delta G0 of the reaction in kilocalorie, this value, minus, this is the value of R when we're dealing with kilocalorie, type 298, and this is constant. So we obtain now a different constant. Delta G0R equals minus 1.364 log K. So now we can also calculate K, if we don't have a value for it, from the free energy of formation, the standard free energy of formation of the ions and molecules that are in the reaction. So this is extremely important, so that you know that scientists, if they don't have a value for K that's determined in the laboratory, they can calculate it from data, thermodynamic data that you can find in thermodynamic books. So this will finish this lecture, short lecture. Next lecture, we will start something different.